Hello, our names are Evelyn, Esteban, and Sebastian, and in this video we are going to talk about synchronous compensator in HVDC inverter stations. The first thing we need to know is what is a HVDC system. A high voltage direct current is a system used in the transmission of large amount of electricity over long distances, and its operation basically consists, as we can see in this figure, in a step-up transformer that will elevate the voltage because we are talking about high voltages. Then we will have a rectifier that will convert the alternating current into direct current, and then this direct current will pass through the transmission lines, and then an inverter will convert that direct current into alternating current again, and finally an step-down transformer will decrease the voltage. Some examples of these systems are found in Paraguay and Brazil. What is a synchronous compensator? It's a rotating machine that works as a motor under no load, and this machine will stabilize the electrical grid by controlling reactive power to manage voltage, providing inertia for frequency support, but increasing fault current. And how is this synchronous compensator helping? Well, basically, the compensator will make three important tasks that are: first, increase the ESCR, that is basically like a measure to sense the grid strength. The second thing is keep high voltage during faults, what reduce probability of commutation trouble. And third, will provide emergency reactive power.
Let's talk about each of the phenomena mentioned in the article with the purpose of explaining the amplified. The first effect is increase of effective short circuit rate and short circuit current. When a synchronic condenser is installed, the effective short circuit rate increases, which is an indicator of how strong the AC system is when supporting an HVDC link. A higher effective short circuit rate means the grid has better capability to handle reactive power demand and operate more stability under disturbance. The result is a stronger and more reliable resin system. However, adding a synchronic condenser holds increase the short circuit current because the device contributing additional current during faults. For the reason, it is necessary to ensure that the system, rotation, device, and circuit breakers can safely enter this higher false current without exceeding their rates limits. The second effect is the voltage support during the faults. One of the main benefits of the synchronous condenser is ability to sustain the voltage during an AC faults, which help prevent commutation failures in the HVDC inverters. In the article, the system calls only tolerance a 40% voltage drop before the condenser was installed, but after adding it, the system can handle drops of up to 28%. This happens because the condenser enters a strong excitation state during the faults, delivering large amounts of power almost instantly. As a result, it prevents the voltage from collapsing, maintains the inverter's commutation margin, and enables the system voltage to recover much faster once the fault is cleared.
Okay, so when we are talking about emergency reactive power, it means that the compensator will provide a reactive power output in case of a fault. As we can see in these two figures, during the fault, the voltage will decrease, and as long as the voltage decreases, the reactive power will increase because of the compensator. And the most important thing we need to notice here is that before we have the compensator, it takes 4 seconds to the voltage to return to its normal value, while with the compensator it only takes 3.3 seconds. And it's very important to the grid that the voltage stabilizes quickly because as faster as the voltage returns to its normal value, the grid will be more stable and stronger.
The impact of T prime. T prime is the direct axis transient time constant. In a synchronous condenser, think of it as the speed knob for how fast the machine's internal EMF reacts to an excitation change after a voltage drop. Why does it matter here? In an HVDC inverter station connected to a weak AC grid, the risk is commutation failure when bus voltage sags. Adding a synchronous condenser helps, but how fast it helps depends on TD prime. With a lower TD prime, the condenser ramps its MVR quickly, the voltage dip is shorter, the bus recovers faster, and the inverter keeps its commutation margin. With a higher TD prime, you end up at the same voltage, but you get there more slowly, leaving a longer vulnerable window. As you can see in this image, the lower the TD prime is, the faster the system responds to recover its voltage. And in the equation, it is consistent. TD is in the denominator. In summary, the synchronous condenser makes the inverter box more robust, short circuit current raises a bit, while the minimum voltage during faults is higher, and commutation failure risk drops. In the study, the allowable dip roughly doubled, and the bus recovered faster. Crucially, choosing a TD prime doesn't change final voltage support, but it gets you faster, shrinking the vulnerable window for the HVDC inverter. Thank you.